everyone. This video is going to be constructing the parent trig functions. So when we have a parabola and there's no shift, its vertex is at the origin. When you have an absolute value graph and there's no shift, its vertex is at the origin, and so on and so forth. So of course, coming up soon, we will be doing shifts and translations of all these trig functions, but for right now, we're gonna just do the very basic, what do they look like and how do you get them? So the first one we're gonna look at is y equals the sine of x. Your book uses x. Most people tend to use theta, remember, Theta, Greek, it's just a Greek letter that we use to denote angles. So I'll be using that primarily, as will most other textbooks besides this one. So whenever we learn to graph a new function, we tend to make a table of values, which hopefully we won't be doing that forever. So we have theta and the sine of theta. And for purposes of trying to keep the video short, I'm going to do the plugging in for you. I highly recommend that you push pause, you get your unit circle out, and you start to plot points like we would have done had we been together in class. If theta is 0, the sine of 0 is 0. 90 degrees, and then 180, 270, 360. We're going to go back and forth between degrees and radians quite a bit. So just for construction, we'll stick to degrees, but later on we'll practice a lot more with radians. The sine of 90 degrees is 1. I don't know. That looks good. So I'm doing every third line on the grid is 30 degrees. So I'm gonna do the third line, therefore would be 90. At 180, we're back to 0. 180, we're back to 0. And then 270, if you look on your unit circle, which you should have sitting next to you, 270 is -1. And then at 360, we go back to 0. Okay, so we've got these 5 points. It is absolutely not a line. It is a curve, and we could keep going. We could say what would be next would be 450. Which would be the same as 90. And after that would be 540, which would be the same as 180. So we call these functions cyclical. You go around the unit circle, but then what happens? You go around again, and again, and so you create what are called sine waves. And you'll see sine waves all over the real world. Sine waves are in sound. Sine waves can be found in when you calculate sunrise and sunset times, high tide and low tide. Have you ever seen when they have a patient who's running on the treadmill and they have all those weird like suction cup thingies attached to their chest? That's called an EKG, and those are sine waves. Lie detector tests, those are all sine waves. So sine waves can be found all over the place in the real world. The most common place that you might see them is sound. So for those of you who play an instrument, higher pitched notes have a shorter sine, the length of the wave is shorter, and lower sounds, the length of the wave is more spread out. We'll talk about that soon. You know what's great is that on graph paper, I can draw a pretty good curve, unlike if I was doing it on the board. So this is your parent sine wave, and it has a couple key features. One of them is called the period. So you know how I just said that higher pitched notes, the wave is more compressed. In lower pitched notes, the wave is more spread out, and that's called the wavelength. Make sense? Yeah? If it's closer together, the wave is compressed, wavelength is shorter, and a lower pitched note, the wavelength is longer. So it's called wavelength. And for the parent function, the wavelength is 360 degrees or 2 pi. So the wavelength is 360 degrees or 2 pi. This is more commonly called the period. And then it has something else called amplitude. And amplitude is half of the height of the wave. So the height of the parent sine curve, from -1 to 1, that's a total of 2. Agreed? From -1 to 1 or 1 to -1, that height is 2. So the amplitude is half of that, which is 1. Half the height, which is 1. Okay? There is your parent sine curve. So just like the parent parabolas and rational function and cubics and all those, you need to know the parent function. Cosine looks very, very similar. Cosine, high point is 1, low point is -1. So let me draw my handy dandy circle here. Around and around and around. So what do you think the period's going to be? Yes, the period's going to be 360, also known as 2 pi. You should pause the video right here. You should try to construct the cosine wave on your own, and then come back to see if you've done it right. There is your parent cosine curve. Period is 2 pi, 360. And the amplitude is 1. Okay, tangent. Everybody loves a tangent. How do you construct a tangent curve? Go back to your unit circle. Tangent is sine over cosine. Denominators cause problems. They always do. You can't divide by 0 ever, ever, ever in your entire math life. No division by 0. Ever. So if the cosine is 0, that creates problems. So if the cosine is 0, then the tangent is undefined. And undefined shows up as everybody's favorite, an asymptote with the silent P. Okay, so what I'm going to do is I'm going to very lightly draw in a cosine curve. I'm using an erasable pen so I can erase this if I need to. That's a cosine curve. Where is the cosine 0? The cosine is 0 at 90 degrees. Asymptote. The cosine is also 0 at 270. All right, if I'm going backwards, if I'm going in the negative direction, that would be negative 90 degrees. negative 270, etc. Okay, so sine over cosine. If cosine is 1, then we get the value for the sine. So the cosine is 1 here. Oh, sorry, we need to put it there. So this is a tangent function. The sine is 0. Sine is 0 at 180. 0 over whatever except 0 is 0. Sine is 0 at 360, therefore the tangent is 0. Sine is 0 at 0, therefore the tangent of 0 is 0. That's a lot of zeros. Okay, so I have an erasable pen. I'm going to erase all this stuff that I just drew here. All right, so I have these waves. Do these two waves look the same? I think they do. And I think that if I were to continue drawing this tangent curve, it would go like such and like such and over here. Would you agree with that? They all look the same? Okay. So the period of tangent is different than the period of sine and cosine. And the period of tangent is, if I can find a better color, from negative 90 to 90, which is 180 degrees. And that's because if you look at your unit circle, the value of the tangent in the first quadrant is positive. The value of the tangent in the second quadrant is negative. But when you go to the third quadrant, everything repeats. When you get to the third quadrant, everything repeats. So if I start at 0, and then 90, and then 180, it only takes 2 quadrants to get through every value I can possibly get through. Therefore, the period of the tangent function is 180. And then here's a trick question. Amplitude, half the height. Well, up to infinity? Negative infinity? What's the height from negative infinity to positive infinity? Yeah, it doesn't make a whole lot of sense, does it? Is that to infinity? To infinity and beyond. Get it? Anyway, negative infinity all the way up to positive infinity, there is no wave. I mean, there is no amplitude. You can't put a value on a height of the largest thing that there is mathematically, which is infinity. So we say that the amplitude of a tangent curve, I hope you can see this, the amplitude of a tangent curve does not exist. The amplitude of the tangent curve does not exist. So overall, in the big picture, the parent tangent curve, because this is too many. This is too many. I only want one wave. It repeats, 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 repeats. The parent function of the tangent curve is, okay, pretend I'm erasing all that. The parent tangent curve is right here. That's the parent tangent curve. All right, see you next time.